Are you SYD anyway? That's right? Okay. All right. That's probably why I haven't had a good day today, is because I've been stuck inside all day. So I should go outside. Yes, Christine. It would have gone to whatever is in your, whatever email you have with G, well, whatever your BYU email is, that's where it should have gone. But so, yeah. If not, we'll get the score up soon. So, yeah. So you're probably not the only one. So, all right, let's get started. Flat tower. Who'd like to have a prayer for us? No one feeling grateful after that exam? I was impressed how well you guys did. So. Anyone? Anyone? Oh wait, who was it? Here, we'll go with Heather over here. It was a tie.
Bless us that we're able to retain all this information that we're learning today and review the things that we've gone over in the past.
Amen. Thank you. All right. So when you came in, you should have been given a worksheet. Michelle has them in the back there. This is what we're going to be focusing on today. So let's start off and start doing as much as you can. Then we'll talk about a few things, and then we'll turn you guys loose again to see if you can finish up, and then we'll plan on coming back. So, and for those of you online, for those of you on Zoom, the worksheet is on, or if you guys that are here want to find an electronic copy, it's on Learning Suite under the pre-lecture material under today. It says like in-class worksheet or something like that. Okay, we found our first typo. It's on 2B. It was supposed to be 3 times in the y direction and 2 times in the x direction. So thanks. Sorry about that. To help you with number one on the proof, I rewrote the definition of a linear transformation up here. So up here on the board. Yeah. All right, people were really struggling with this first part, this proof. So a lot of you did a great job of rewriting the transformation. A negative x plus 2y, a minus y minus 5z, and a minus z. A lot of you did a good job of rewriting this as a vector xyz times a matrix, which is awesome. We use this a lot, but it's not what you use for this problem to prove it. So at least to prove it from the definition. Once you have a theorem that says any linear transformation can be represented as a matrix multiplication, any matrix multiplication can be represented as a matrix transformation, then that is enough to prove it. But we want to have practice proving from the definition here. I know a lot of you are weak on your proving skills. So this is kind of a nice structured proof that you can work with. So this is a minus 1 in the x. There's no x's there. There's no x's there. I have 2 y's. I have a negative 1 y, and I have 0 y's. And I have no z's. I have a negative 5 z's, and I have a minus 1 z's. Okay? So a lot of you are good at translating to this. That's good. But to show that it's linear transformation, we have to show that t of the sum of any two vectors is the same as the transformation of the first vector plus the transformation of the second vector. And we also have to show the transformation of a scalar multiple of that vector is the same as the scalar multiple of the transformation of the vector. So this is the start of number 1. I'd like to show it's first. I picked two vectors, u and v, and just called them x1, y1, z1, x2, y1, y2, z2. And I started to look at, hey, what is t of u plus v? Well, here's u plus v right here. And then I put those in to everywhere there was an x, I put in x1 plus x2. Everywhere there was a y, I put in y1 plus y2. Then you're going to use some of the properties you know of matrices and operations to see if you can rewrite it so you have t of u plus t of v. Okay, so it will hopefully help you on your way on that first one. Okay, continue working. Okay, there's some questions about the shear transformation. So let's explain what a shear is. So a shear transformation keeps one line fixed. So let's say we're going to keep the x-axis fixed, and then all the lines that are perpendicular to that, it starts to what's this action? Starts to lay them down or something. So they're like your blinds, the leveler blinds or whatever. You have all your blinds like this, and then you have the piece that's connected to all of them, and you move that up and down, and they open and close. So that's the kind of stuff that's happening here. So all of these lines, they get sheared and they go this way. When the point where they cross the line that's fixed stays, and then the angle of all these is the same. So you can think about, all you need to do is thinking about one point and where it goes. That's not the best example here. So I can think about where this point goes to here. In this situation, this point doesn't move. So I can use those 2 points to figure out where the whole thing goes. It doesn't have to be the x-axis or y-axis. That's. Let me borrow my good one here. I could have another line like this and think about lines this way and then shear it. Okay, so that also works. But yeah, it helps the most to think about which line is fixed, and then how far do I move a line this way? And that 1 point moving over is enough to know where everything else goes. Those 2 points are enough to know where everything else goes. So hopefully that's enough to get you going somewhere on that. Okay, here's shearing by Bart. Okay, if you want to look up. So here we have our friend Bart, and this is a shear, just like that. That is a shear. So I can keep going. That's more extreme of a shear. Okay. Notice the points of Bart that were on the x-axis stays the same. So in that situation, the x-axis stays the same, and then all of the lines that were perpendicular to it are no longer perpendicular. This is a shear in the other direction, so the y-axis is fixed now, and then Bart gets sheared the other way. So, and to think about how far I go, like in this situation, remember the key theorem here about finding out the matrix that does the transformation is to think about where does 1, 0 and 0, 1 go? Where do our basis vectors go, our standard basis vectors? So in this one, look, my standard basis vectors are 0, 1 and 1, 0, sorry, 1, 0 and 0, 1. 0, 1 stays the same. That's why in the matrix there, that T, that second column is still 0, 1. Where does this 1 go? This 1, 0 go? It's the x coordinate's still the same, but it goes up to about y equals a half, or 0.6. So it goes from 1, 0 to 1.6. 1 and 0.6, not 1.6. So that's how I know, that's how I can figure out what the matrix transformation is. So that help? Okay. Do you have any of these done?
Yeah, I got up to here. I just can't remember what the projection matrix is.
Oh, but this one you did, right? All right. I'm just going to go through a few things, a few slides, and then we'll go through these problems. And because I know some of you are struggling. Just quickly, linear transformations. I can't remember if I mentioned this I got to mention this in this section or not, but yesterday. But they keep lines as lines, and they keep the origin as fixed. They're not all transformations, possible transformations, but they are some very important ones. A translation, like a shift, where you're just shifting all of the points in one direction, that is not a linear transformation. It does keep lines as lines, but it doesn't fix the origin. There is a trick, mention this here, there is a trick to use an extra dimension, and then you can write translations in a lower dimension as a projection of a linear transformation in a higher dimension. That's what animators do, 3D animators and roboticists, I don't know what you call a robotics person does. They're called homogeneous coordinates. And all possible linear transformations can be written as a matrix multiplication and vice versa. Okay, one of the things that you may not have picked up from the reading, so we can do composition of translations. We did mention this before, that I can do a rotation and then I can do a stretch. And if I can find the matrix representation for the rotation and the matrix representation for the stretch in a certain direction, then I can just multiply those two together to get a transformation that does both of those at the same time. But you have to be careful about how you multiply these together, because the order might change the transformation. So if I do t and then s on a vector, I need to make sure t is the one I multiply by that vector first, because we're putting the vector on the right. So t and then s is s times t times x. So it can be a little bit, can throw you off a little bit there. Also, one of your homework problems, it has you show that you can do the substitution method or the multiplication method. So you're used to doing substitution with regular functions, right? F of g of x, I take the thing that's g, 2x minus 3, and I plug it in for x, right? That's what you're used to. You can do the same thing here without doing the multiplication, although the multiplication is easier. But I want to convince you, there's a problem here, so you can convince yourself that it works. So if I have a transformation that's t, I have a transformation that's s. What's s of t of x, or s of t of x and y? I take my x, so I take s, that's my second one, and I have to plug in what I got from my first one. So s, the x coordinate is 2 times the old y coordinate, and the old y coordinate is x plus y, because that's what I got first from doing the t. So the x plus y gets plugged into my y there, so I get 2 times x plus y. That's what happens if I do t first and then s. So you're doing substitutions. I feel like I need a marker here to show you where things are going. But the s transformation here, the new y is 3 times the old x, but the old x is the new x in t, which is x minus y. So I take x minus y, plug it into where the new x is with that 3, and you get 3 times x minus y, and then you guys are good at going from here to there, and you get that matrix multiplication. And that's exactly the same as if you multiply, but you can also get it with the substitution. So there's one homework problem like that. Well, we'll come back to that. Okay, let's do, all right, so here's the rest of this proof. So just to recap, I picked a u and a v. These have to be arbitrary. I'm not going to pick just one specific one for u and one specific one for v, because it might work for just those specifics, but not in general. So you have to pick general ones here. So I picked general ones for u and v, added them together, put them into the particular transformation here, and then we start doing the algebra in here, the arithmetic. So multiplying the 2 out, distributing the negative. So then you can start combining all of the ones that have a sub 1 and all of the terms that have a sub 2. So that's what we've done here. And then we're going to write those as 2 vectors here. So these are all the sub 1s and these are all the sub 2s, but then I can rewrite that as, this is just T of U, and this is just T of V. Right, if I just plug in x2, y2, and z2 in where there's x, y, and z, then I get this. So, and same thing if I plug in x1, y1, and z1 into here, I just get T of U. So they're the same. And then similar process with C. I just need one vector now, so I'm picking, I don't have to have my my indices there. So just pick an arbitrary x, y, and z. So plug in C times that, and then pull out the C's. You can pull out the C one more time, and you get this, which is C times T of V. So, okay. This is the kind of proof that could be on the next exam, okay? So you'll see this on your homework. You've seen it in class. So like, once you see it 2 or 3 times, you might expect it to be on there. And this is structured enough that we'd expect you to be able to do something like this on the exam, okay? So questions about this? Yes? I'm saying U plus V, I'm going to pick some X, Y's, and Z. I'm going to pick some individual values here, because so I can start using this. And so the individual values I pick for U are just going to be X1, Y1, Z1. And the individual values for V are going to be X2, Y2, Z2. And then those are going to add up to your original X. So the U plus V here, I'm going to rewrite it this way. And then I can apply this transformation. This transformation says my new X is my old X. I subtract my old X and add 2 of my old Y. So my new X over here is I subtract my old X, which is this, and add 2 of my old Y. So I did that. And then same thing here. My new Y is I subtract my old Y. So here's my old Y. I subtracted that. And I subtract 5 times my old Z. So here's my old Z. I subtracted 5 times that. Yeah, so I didn't do it again. We just started to distribute things. So I distribute that negative to get negative x1, negative x2. Because I want to pull all the x1s and y1s and z1s together. And I want to pull all the y2s and x2s and z2s together. Yeah, so we did the distribution thing. And then now we can start grouping all of the y1s and all of the sub 1s and all of the sub 2s. Okay. Oh, gotcha. Great. Okay, other questions about these? Yes, Heather? Oh, you can do it the other way around if you want. Okay, so it was, can I go CT of V and eventually get to TC of V? Yeah, you can do that way too if you want. Good question. Other questions? Okay. All right, this first one, we're trying to move the eyebrows and the eyes over. And so the y-coordinate doesn't change. Y-coordinate stays the same when we reflect it across the y-axis. So that's where I have my 0, 1 here. But the x-coordinate, it changes just by a sign. So change the sign of the x. So I get -1, 0, 0, 1. You can, so some of you were able to just think through it this way. This one isn't too bad. But you can go back to the theorem and think, okay, well, if I'm reflecting along the x-axis, I can think about where does 1, 0 go and where does 0, 1 go, and to use our theorem. It says, okay, where does this go? Well, that's going to go to -1, 0. So that's going to be the first the first column of my transformation matrix. Where does 0, 1 go when I reflect it along that line? Well, it's on that line. It doesn't change. So I just go like that. So it stays. So that's the power of that theorem, where you can just think about what happens to your standard basis vectors, and then write where they go in these columns. So, all right. So this one, we're doing another reflection, and then we're stretching it. So to make it easier to think about, I said you could just think about it in this form here. So, so here we're going to reflect, and Tanner stretched it 3 times in the y, doing this. So any point here, I have to change the sign of the y, but then stretch it 3 times. So that's the negative 3y. And where's his 2? Oh, he illustrates the 2 one down here, that you're going to stretch it out twice that far, so you get the 2. So you may not have thought about it this way, but this is a perfectly viable way of thinking about it. A lot of you probably did 2. Well, I should ask, did any of you do 2 matrices here and then multiply them to figure out what your last matrix was? Okay, so some of you did that. Perfect. That's why I put this on here. So first you can think about the reflection. What's the reflection along the x-axis? Then you get 1, 0 stays the same. The y-coordinate changes sign. So that's the first thing. And then you can stretch in the 3 times in the y direction. So you can do this in terms of, you can do it three products if you want, yeah. And then stretch in the x direction, and then you can multiply those all together, and you get that. So very nice. Good thinking going there. Questions on this one? Yes?
Yeah, so it is kind of like you're showing that
Oof. Hold on, I made this. I put these in the wrong order. In this case, I don't know if it makes a mistake, but it makes a difference. But yeah, so I know these don't matter, the stretching ones, but 1, 0, 0, 3. Okay, thanks. And these. Yeah, so this is the first action I do. Then this represents the second action that I do, and this represents the third, because the points I'm multiplying by are a vector over here. So I do this first. It doesn't matter when I'm actually calculating. I can multiply these 2, and then I can multiply these 2, but the action will be the same. It'll be the same as if I multiply these 2 together, then these 2 times that, this times that product, then this times that product. I have to put them in this order. I mean, sometimes it doesn't matter, but we do know matrix multiplication isn't commutative in general, so you should always be careful. In this case, I don't think it matters. But yes?
So how do we know then which transformation to do first?
I mean, if you're doing multiple transformations? So that,
Yeah.
yeah, so it'll tell you, like in the statement of the problem, well, do this and then do this and then do this. Yeah. So sometimes it doesn't, some of them don't matter, but yeah, just in case, you should be careful. Okay, other questions on this one? Okay, so the rotation one. So a lot of you, you remembered from the book, it talked about this matrix on how to do rotations. A couple people asked, where did this come from? So if you didn't know this and you had this problem on the exam, what would you do? You shouldn't be lost. Okay, you don't have to have this memorized to do this problem. You just have to use the theorem. Oh, where are my vectors? Where are my standard basis vectors? Where do they go if I rotate them 30 degrees? Well, this one's going to go something like that. This one will go something like that. And then I just have to figure out where these points are, and I can do that with geometry. So I know the length is 1 here. I know the length is 1 there. I know this is 30 degrees here, so I have a 30, 60, 90. And here I have, that's 30, so this is 60. So then I can start doing my trigonometry. So the ratio of sides is 1, 2, and the square root of 3. So 1, 2, square root of 3. So I have to cut each of these in half. So this is up 1/2. This is the square root of 3 over 2. So this point right here will be, I have an x coordinate of the square root of 3 over 2, and I have a y coordinate of 1/2. So even if I didn't know this, a lot of you, even if you know this, when you put 30 degrees in there, you don't know what cosine of 30 degrees is. So it doesn't help you anyway. All right, I'm just kidding. I'm not like not mocking you, right? I don't know what it is off the top of my head. I have to sit and draw a triangle. So just like this. So, and then how about this one? I can figure out what that is. I'm not going to take the time to go through it, but it's the same idea. And where does this come from? It comes from exactly doing this with an unknown angle. So just take your arbitrary, take your two basis vectors and rotate them an arbitrary angle. And since this is 1, what is this length? That is sine of theta. What is this length? It is cosine of theta, right? Think it back to the unit circle. And what about this length? Well, we're going in the negative direction. And here, I'm not going to think about theta here. This is 90 minus theta, but this theta using transversals is the same. So this opposite side is going to be sine, but it's going to be a negative sine of theta, and this will be cosine of theta. So, and then those become the coordinates of those points. This is I go cosine over, I go sine up, go negative sine over, I go cosine up. Yes? Shearing is not the same as rotating. So, yeah, shearing is not the same as rotating. So, for a particular segment, you might be able to do a certain rotate and stretch thing to get it look the same as a shear, but they're not the same. So, for example, a shear is something like 1, 1, 0, 1. This is a shear. That's not the same form that we have here. So, do we have time to do the shear? Is the next one the shear? So it's the next one, the projection. Projection is probably more important than the shear, but whatever we don't get to, I can make a video of and I can post it. All right, let's do the projection. Okay, so we have the line y equals 1/10 x. And we're projecting, so projections are always perpendicular. We're projecting onto this line. So again, I'm going to start with my 1, 0 and start with my 0, 1. And I have to just think about where are these going to go when I project perpendicularly. So I need to find this point and I need to find that point. And we know how to do this. Like second day of class, third day of class, we learned about how to do dot products to project onto a line. Well, technically onto a vector, but hey, let's just draw a vector on this line. So 10, 1. That's a nice long vector here, and I don't have to worry about decimals or fractions. So now let's project each of these onto 10, 1. So (1, 0) dot 10, 1. I'm going on to 10, 1, so that's my denominator here. 10, 1. So this will give me that's the vector that goes to that spot right there. And the other one is 1, 0, 1, 10, 1, 10, 1, 10, 1, 10, 1. It's going to be just some scaled version of this vector, right? They're both on that line. So if I multiply this out, what do I get? 10, 10, 0. Here I get 100 plus 1. So 101 times 10 times 1. So I get 100 101s, is that right? And 101. No, and then 10 over, oops, 10 101. Okay, so this point here, I don't move over, I don't get very much shorter, 101th that distance from this point. It doesn't, this line is much flatter than I've drawn it, so. And I don't change, don't change much there. But and then you can do the same thing here. So our final thing would be 100 101 10 101. What's the other column that you got, Philip? Do you have it right there? Sorry, what is it? 1 over 101. Oh, so this is like super steep right here. So it's like way down here. Okay, so there's a projection. Kind of from scratch. There is a formula in the book for doing it, but I don't remember those formulas. Understand what it is from scratch. You can just do it when you need it. Okay, we're out of time. I'll put up one, that shearing one, I could put up an example video so you can see it. Have a great day. May your frowns be turned upside down.